The problem with physics is that it's hard to convince the process, to that it's able to be just how the process works. Because the way we engage things is we relax. Like we have to really just read through papers and we have to just write down our observations, write down all the recollections. Like the job of a physicist is to be a categorizationalist. Like we just look at information of the world around us and like we just tell you about it. Like we whatever question you're trying to contact us for or have us help you through, it's it's a hard one to express. It's one that is just a you gotta relax. That's what it's about. Um, so I just wanted to explain the research process and how that's going to be something I'm going to start doing more often. I'm going to be showing you guys like end of the day reports of what I was reading through and what I wrote and the analysis of it, because I want to make this a lot more of a public and transparent process, how the difficulty of it works, because it's hard to convince companies the utility of physicists if you don't necessarily advocate for and demonstrate how the work is done. So how we do it is I would read through a paper. So right now I'm currently going through optimization frameworks for graph clustering by Nate Veldt. I saw his PhD defense on YouTube and I thought it was really good because I saw tons of connections to particle physics. Let's see if I can flip the camera. But so the point was that I saw that his paper had a lot of connections to physics. And so because of that, I'm just going through that. And that's what I would do in my real job, if I was directly hired for or contracted as a physicist. So physicists are kind of like a very specific niche category. We invent things and we bring designs to fruition. But the process is done by taking your time. Like mostly what we do is we set up information spaces. So often we use the right hand rules from mathematics. We use that sort of in everything. We try to apply and find an information space of which to manipulate the information or the data within that information space. You can understand how, in a very rudimentary sense, yes, physicists are just motion engineers. We're just engineers that teach you how to get from object A to object B, and then the engineers build it. Yes, but we're more than that. We're the people that if you want to make sure that happens, I tell you how that's done. So what that means is that physicists have been contracted for point A to point B. Hey, design an aircraft, design a plane or something that can do that. But then engineers forget to apply physicist rules, and they forget to protect the person from point A to point B, or complete the action exactly from point A to point B. They don't keep the goal of doing that because they don't believe it's physically possible or within capabilities or feasibility. It entirely is. And that is our job as physicists. So by going through this, I'm currently breaking through the standard model and just trying to explain how that works. But that's just research stuff. That's just personal research that one would be hired for as a physicist. If there's any questions about what the daily activities is, or at least what it's like to contract a physicist, that's sort of what this is about right now. I'm going to go back to reading the paper and explaining what I see from it. But I want to give TikTok end of the day reports, or at least end of like a period reports of like if I think it was significant. Like, all right, so this is sort of what I got so far, and this is what I was reading. So you can use these things. That's sort of all we do as physicists. We're like consultants. We're like mathematical consultants for engineers. It's a very specific niche. If there's any questions or if you'd like to join to ask questions about this, I would be more than happy to, or more than willing to converse. So I'm going to go back to doing research. which is kind of weird because it's like now I'm being watched, but I'm just gonna read. So if you wanna talk, we'll talk, but I'll shut it down in like 2 minutes. Just like it's like office hours. It's office hours right now. If you have any questions. I guess it is office hours. Fuck, dude, I'm gonna start doing that. We're gonna start doing office hours. Okay, because that's basically what you can ask. Hey, professor, like, what are you looking at? Like, what are you researching? And they'll be like, oh, well, I'm just looking at these two things. Like, I'm just like, you wouldn't understand it. And then he was like, yeah, I would. The fuck, explain it, man. Like, so so that one guy that I was like talking about inspiration from about analytical mechanics. My analytical mechanics professor, I just asked him like, what does he do? Like, what is the forefront of physics in terms of like that nature, in terms of like these calculations? Like, if we know everything now, like, can't we really predict stuff? But he's like trying to do the analytical mechanics, but more like analytical dynamics. It's like even more crazier than just mechanics of like regular. Like we think about them as like flat 2D waves in space when you calculate them, like the integrals of them. But he wanted to do like a path integral. So he wanted to solve like the dynamics for actions. So he wanted to solve the electrodynamics and the wave mechanics of dynamic systems like neurons. He specifically wanted to study the electrodynamics of them. So at first I was like, so it's wave because it's like information across time, across space. Because if you start in a region, then it is a wave. You get me? Because it has to travel outwards at a rate at the speed of light, at the friction, as the waves travel through dielectrics. So he had to consider that. And he also had to consider so that's why you can see how the functions are building from the same stuff that he said the same stuff you are learning in analytical mechanics is the same stuff that we do. There's nothing special. You can do this. But it's hard. I was like, yeah, that sounds really damn hard, man. I was like, that's cool. So specifically, he was doing the electrodynamics of it because wave mechanics is just hard to replicate in the lab. But so if he actually sends a pulse, so they're actually pulsing data. So what they really want to understand and basically do the Fourier analysis is to decompose like that kind of data, wave data. But we already can do Fouriers for like one direction in space. You get me? But he was trying to do Fouriers for like 3D space. Yeah. And so I think like you can clearly see how that problem would basically take like actually I want to start working on that. That actually sounds like a good thing. So I'm gonna start touching that because I can see how it would be done. Why not? If you can do it, let's do it. Just see what he was looking at. That's the cool thing. You could just look at wherever any other physicist is looking at. That's our job. Like you have to be able to like, well, jump up ideas and go look at something else because you asked me to. I was thinking 3D when you said route integral. Yeah. It is path. So yeah, after I learned like path integrals and like in Calc 3 at UCLA, like sorry, I look really messed up today. But yeah, once you learn like Calc 3, I was immediately thinking about like trying to move like vectors in space, like kind of like draw a 3D line, like how you would compute it that way. Yeah, I was thinking about that. And I was realizing something earlier that you can represent that kind of path space. I was actually working on that. I think that should be a classic physics problem that every student should do. Because that really demonstrates like your advanced knowledge. It's like I'm working on it over here somewhere. Let me get it. How are you guys doing right now? I'm just trying to bring you up my notes. I guess like how a professor would like, okay, let me find my paper. Yeah, okay. So if you want to code stuff a lot more efficiently, you need to ask a physicist. This is what I'm trying to explain. So physicists, what do we do? So, okay, so what the problem is right now is that as soon as we were thinking about path integral, we need to think about how to think about how to move through space. And so I was just trying to solve the problem of like a render. So if you wanted to do a render very efficiently, like this is why I'm telling about this is information physics right now. So if you want to, oh, you are in office hours. This is what this is. Okay, cool. We're in office hours right now. You're my student now, and I'm the professor. So currently researching, I'm working on, is how to render efficiently, like the cost, like the calculation decisions of like analysis space for a predator and a prey. So I'm trying to code like the motion mechanics of this thing where it can move in three-dimensional space, in all 3D space. And it's going to hunt that thing. But they have to do with physical laws. You get me? This is literally how, like, if you can solve this in one go, if you can code this physics, like, dynamics in one go, you will vastly improve, like, computation speed and power, because you realize how you don't need to even calculate forces. You don't need to calculate the path integral dynamics. You don't need that. All you need is, like, the potential fields. And the potential fields are known laws. Like, they're simple to calculate. They're simple to integrate. Like, we know how to do that. And if you can convert your information space to this, which you always can, I'm trying to write, basically, because you always can move stuff to information space, what happens is here, if you can solve this problem in like R3, in our universe, if you can solve it in R3, it solves for every, what's it called? Iterative, recursive integral problem, like in 3D space. So because of like my standard model prediction of like how you can speed up computation speed, it basically helps do all of that. It helps make stuff more efficient if we can just solve this recursive integral, coordinate system, recursive coordinate system. So right now we're trying to imagine the 3D space about the forces, and all this is sort of like evaluating the flight dynamics. All right, so if you look at linear algebra, so now we're going to go into vector space. We're going to understand how this relates to ideas and information. So in quantum mechanics, we talk about two different vector spaces of possibility. And that can be represented as cosine and sine, these relationships. Because like cosine and sine have themselves an infinite like span of possibility, like this is how you can extend your dimensions. Like it's just information. Quantum mechanics is the study literally of information. So like it scales to everything. So I think you really need to understand like how to do the linear algebra / how to do the quantum mechanics how to do the physics of quantum mechanics. If you can do that, then you would be really good at coding. All right. So what else? Okay. Here. Okay. So I wanted to talk about using like that processor, the multiple matrix processor of chips. This is what the future coders have to know. So if you want to code in this special R3 that has all these like efficient properties, you need to understand how to decompose each vector, each of these like main vectors of XYZ space, like that you would normally represent computationally, like as a, you get me? Like this is like your path. XYZ is your path, your travel path. But you need to represent that in terms of these inner quotients or inner functions. And if you trace your movement path in 3D space, like your big, like this is like your character motion. So the big values are your character position values. So that's what that means. And the inner ones are your like reference modifiers in a way. You get me? They're like your force modifiers. These are functions that you can apply, that you know the rules of by physics. You can plot the calculation trajectories of each of these. So if you can plot the trajectories of each of these, and you can, then now you have the higher form. And now that you have the higher form, you can easily integrate that. It's literally differential equations. Like, you get me? So if you can solve your coordinate problem, you can then solve everything a lot simpler, a lot quicker. And this would just use matrices. These are just matrices in terms of like the computer can easily calculate this. And this is the future of computing. You're going to have to know this if you want to be the new software things that I was talking about in the most recent video. And there's also another quantity. Now this one is computationally expensive, but it's
it sort of has to be done. This is like your motion, your momenta, and that this is your angular momentum. But we're not trying to define it as angular momentum. We're trying to just define it as like continuous momentum of these upper derivatives or upper functions. And if you want to solve this, the simplest way or the way to solve this is to just do a flight dynamics sort of illusion. And that's how it works. So you decompose your problem. So this is like electrodynamics. I was just trying to explain what we were doing in electrodynamics and how it relates to your integral of J. We had to solve this problem by Professor Bacchus at UCLA. He was really, really hard. Like he was difficult. He basically tried to tell us like how to decompose like your problem. It's cold. So how to decompose your problem from like, suppose your current is at R prime and it goes up along the wire, but you are at R. So what is the sum of the forces that you would feel at R? And I was like, holy fuck, that just sounds like ridiculously expensive. You got to do the numerical analysis of each of them. Not that it's not possible. It's just that sounds like a really difficult integral. Like, can it be done? And then yeah, it can. It's just like it's fascinating how that is related to what's it called. And that's where it gets even harder. So Bacchus started with this. This is just coordinates. He said, the coordinates are simple. Coordinate analysis is simple. It's the integration that kills. I was like, damn. he was pretty crazy, bro. He was really good at his job. So what's the law that I'm talking? Biot-Savart law. So for Biot-Savart law, you have to integrate from all of like the applicable space, which is going to be from negative infinity to positive infinity. And now this sort of like gets into like kind of quantum mechanics a little bit, because you need to be able to do those kinds of integrals. So like it's crazy how like the way they taught physics at UCLA was just so fucking perfect. It built on everything. Like, and your world just kept expanding. I was like, there's no way we can do this. Like, every time you get a problem, we always are like, there's no way you can do this, man. How are you guys doing? You guys following along? Like that's how it felt. Like, that's how it feels to be a physicist. You have to be able to, like, see. Like, it's crazy. It's crazy, because, like, these problems are possible, and we know how to navigate you through them. So we're like guiders. We're perfect. We're supposed to be like walkers. Like, we'll walk you through the path. Like, whatever you want to know, I'll walk you through there. Like, yeah, sure. And so you have to then figure out this solution. So he showed us like I don't have it right here offhand, but I tried to come up with it from scratch. I didn't want to just reference my notes because he had the solution, but I didn't want to do that. So I wanted to sort of envision the problem about how we would write this in terms of, I was like, at first I asked him, doesn't this have to be what's it called? Parameter equation? And he's like, no, it doesn't have to be. But for you, it is. I was like, what? So you can write it in absolute phi. Like, and if phi changes, then you can represent phi as proportions of time. So because you can write phi as proportion of time, he writes time up here. You get me? Like, you could just do it in absolute phi, but he wants it to basically say, what if it's moving with velocity? How do you represent that? And I was like, you just add a coefficient. And I was like, no, you don't have to. It's like, because then you're just doing bullshit coefficient stuff. I was like, wait, what? So he basically was teaching us how to represent reality the most efficient way. And I was like, damn, this guy is a real fucking professor. Like, he really understood his stuff. So for me, it was very difficult to just even build this problem. And then we're not even integrating it yet, because the integration is a tricky not a tricky, but like if you see it, like, it's a clever solution. And that's what this is. Physics is just telling you, like, the world around you is not difficult. It just requires a clever solution, like how to view the problem. So because we see this as cosine of, like, this function, like, it's like you sort of start representing them as like an exponential. You know that as r changes as a function of distance, because now you have to look at your problem. So as you look at it as a function of distance, you take it to like a ratio. And he basically told us it's a spherical transformation. So now I need to take this and I need to look up like spherical potentials. I gotta write this down because this is my notes too. This is basically you're here while I'm trying to make notes. So, what's it called? Sphere, sine. So yeah, you take it to another spherical analysis. You basically have to look at it for more derivatives, like more integrals. You look at it from electrodynamics now. So before we were just building this on just like trying to plot a plane. That's all we were trying to do. We're trying to code a fucking plane. But then, in order to even represent technically this function represents the path that the current takes through time, how that path will affect this point. So it's a surface now. And that's how it is. Like you basically you realize how by swapping realities, you learn more about each other. And like, that's what you have to keep doing. You have to keep changing how you view your problem. And then by doing that, by doing that 2 times, you basically solve for like the force function. You solve for the acceleration plane. And then after that, you need to do it one more time to solve for the acceleration forces. And so you see how it works. Like Biot-Savart's law couples to, what was it? Just dimensional coordinate analysis. You see how it couples. And that's physics. That coupling is physics. Well, we know the laws that make them couple, and we know how that works. That's all it is. It's this. It's just learning what coordinates everything is. Like how to look at your right-hand rule and how to remember what laws apply. That's it. Next. All right, so here's the solution. Or at least, let me just close my laptop. What is that? Okay, so if you want to represent this, so this is another thing. If you want to represent what if your current's changing through time? So we didn't go through that. But if you really wanted to, he said that's a problem for grad students. So you would basically now have to represent this as phi, because now we're changing our velocity, our perceived velocity through time. So now we do this through time as a parametric, but we don't need it. We don't have to go through. So you're going to need to add extra. So phi can change in both directions, but it's sorry, never mind. That's the thing. So now we need to add a phi. This is if you want to add force functions. Only if you want to add force functions. But for video game models, you don't need to, because you don't need that accuracy, because you're not trying to process that accuracy because you know the output. Force functions are only for coefficient modifiers to know what changes. You should check the screen share. Oh, wait, for this? Oh, okay. I'll try. Is that possible? On iPad, I guess? Let me put this on. All right, we'll try that. But that's sort of as far as I was going for right now. So, yeah, I'm gonna go back to working, I guess, because I was just trying to read the thing. So what I'm working on, I guess. So yeah, we're done doing yeah, basic what the students would do. Or not students. We're not doing dimensional analysis right now. I'm trying to do decision analysis. So that's like particle group theory, and that's like chemistry. So I'm trying to discover the rules, the chemical rules
for particle physics because it does have those. So I'm trying to also explain how particle physics can then go up to chemistry, like they're roots of each other. You get me? But because I don't have like the chemistry intuition, I can't see past hydrogens. I can only see hydrogen exchange with electrons, which is the quark. I have the solution where you have like a proton like exchange with an electron, and it is like it's like a duality. It has like an extra like a swapping up minus quark, and so because of that, it basically keeps its negative charge. It's basically a W minus particle that owes energy with the proton, and it literally fits the chemical like the chemistry principle of like lowest potential, and also like because it owes energy, it's stable there. Also, they're charges, so it just fits the perfect. It fits everything. So because the electron is not really an electron, but actually this quark pair, it just loops perfectly with like the proton. Now they're in energy exchange, and the next thing I'm trying to do is understand how the proton can be used with its like up down rules with higher quark concepts, with higher quark particles, because helium has the same composition of proton, but in a double form, in a doublet form. And that's what it looks like with the particle theory that I have right now. Like you do have these things, they're not gluons, but that's what's funny about it. They are technically the gluons that particle physicists observe for strong force groupings. That's what I realized. Strong force couplings are just weak force couplings to the third degree, because you can see how it was first. It's the weak force coupling of to assemble the proton. Then it's the weak force coupling to assemble two protons. Then it's the weak force coupling to also have the negative like of their respective electrons, because helium is just two proton, two electron, and also the neutron pair. It just, you can see how it just builds, like the quark pairs start just kind of working together. They're kind of just orbiting each other. They're just there, like they're owing each other, like their energies. They're just flowing. But I'm trying to understand, like, you get me? The dynamics of it. Like, what is the values? How to write it in bit values? How to keep it with still like the rules? And that's because that relates to calculations. So it's crazy how the stuff of particles is actually the stuff of thought and consciousness, because the rules of how they interact is, fuck, I don't have it right now, but the rules of how they interact is roughly so there's you remember the particle physics, the up down. Okay I gotta get my notes for that. But I know what's going on right now. So what I'm trying to evaluate is, in Veldt's paper, he talks about the mathematical reason, which is the same rules that I see in physics. These are the mathematical rules. So I was very happy to see this, that you can sort of describe this relationship as, like, I'm trying to write the states in a mathematically sound way. So though the binary values work for what we have, we need to also make sure like that it can be explained in terms of like probability, because this is what we need to deal with reality. Yes, we can solve this for games, but these are the coefficients. So the coefficients is actually the 1/3. So basically, we're trying to see which quark it is. Is it an up or is it a down quark? And by knowing that rules, because the rules are the same, like these are different exchanges. So this one is an exchange of probably, I'm trying to write this down, maybe it's an up and a strange. I'm trying to evaluate the rules later. I'm just trying to write the connections now. That it seems like it's an evaluation with some of the fundamental particles. I just have to swap them.
It's not a case of if this rule is the rule. We know his 8 cases are the rules. I know that by the limits of the particle physics theory that we have the binaries that work really well for chemistry. And like, you get me? Because it works too damn well, I think that we should invest a little bit more consideration of why math has these fundamental rules where you can change coefficients, and the coefficients happen to be the same coefficients of electric charge that we have in the lab of 2/3. It basically means that, yeah, it's crazy. It's beautiful. It does sound like oneness through harmony. It's pretty cool. But yeah, so that's what I'm trying to do right now. I'm trying to just show and plug in the physics that, like, you get me? Mathematicians just solve things. He basically proved, like, hey, there's this weird rule in, like, set theory that basically that you can always group things in this. It's like, but he didn't know it was always guaranteed. You get me? He wasn't a physicist. We know it's always guaranteed by the rules of linear algebra. But mathematicians don't, because it's a discontinuity. It has to be. Because decisions are a discontinuity. They're conditions. That's all they are. It's conditions of reality. That's why, what's it called? Those infinite things, like the fractals and Mandelbrot sets, that's why they look like that with all the different colors. That's why they're balanced that way. Because they're decisions. They're like, is it positive or negative to my directions? It's like they're really close together. Couplings. I'm gonna get some water. How are you guys doing? How's office hours? So that's what I'm doing right now. And that needs to get done before anything else. That's why I'm spending my time on this as like a public physicist to just research this. Because this is sort of like exactly like Nathan Veldt was doing. He proved something that then people are like, well, what does this mean? And he's just, it is what it is. It works, and it helps your computation stuff get better, I think, because it just, your corollaries in the way the mathematicians and the coders are trying to write machine learning, they're writing the coefficients like physics, but they don't really, you get me? Like, they're just trying to solve things with coefficient, like analysis. Coefficient analysis is brute monkey work calculations. They're doing brute monkey work calculations for no reason. They're wasting computer power. And that's another problem. That's why I do this research. We need to figure out how to better evaluate information. We need to decide sort of how to preserve as much of reality as possible that we're trying to capture in data, while also having the most use with that data. That's what it is. So right now I'm just working publicly, just for you guys, I guess, for the public. That's how I feel, man. That is how I feel. How are you guys doing? Fucking, it's cold. Hello. How's office hours? Any questions, students? They also represent situation examples. Here's what I realized, and I was trying to read through my notes right now. It says when all edges are negative, the bounding is very loose. That means when you have just when all the electric forces are negative, whenever the scalar potentials have like the central point, you can sort of see the fields now. You need to write it like that. So that's what this means. Whenever you have like all your edges are negative, these are sort of like the rules of analysis, which in a way is good to see. When your structure of theory follows the dynamics of dynamics itself, that's when you know like you're sort of in the flow. And that's what mathematicians are doing. That's what they did for us. And now we just keep going. So case 4. We look at the symmetries of this. And this is what the quark theory actually states when I'm trying to explain it. The reason it works is because when you have a 1/3 charge, you have a positive. So suppose there's only a 1/3, so it's 1 minus phi. And this phi happens to be 1/3. So suppose that's the quark of the original charge minus a down, and that becomes an up. Sort of that's how it works. Not exactly, but sorry, I messed up. But that's basically what it is. You can see that it's just an exchange. And that's all this captures. It's an exchange. It's just information. The same rules of here is the same rules of the particle physics theory that we already know. So yeah, I'm gonna go back to just doing my own thing. Sorry, going back to research. All right, bye guys.